Hello everyone, and welcome to this module of the Lyle Business System Yellow Belt. The topic of this class will be standard work, part of the Lyle Business System. What's the definition of standard work? In the context of continuous improvement, standard work is the current best method of performing a task, operation, or process. So my background is in industrial engineering, and very famous, the first practitioner of industrial engineering came up with a concept that there's one best method of doing any type of work. And that was pretty much the point of view for many decades until Lean came along. And then that was slightly modified to say that there's only one current best method of performing a task, operation, or process. So there's always a way of improving on it, but until you improve on it, you want everybody to do it the same way. Okay, standard work is an integral part of the Kaizen process. So in the Kaizen process, you're working off the familiar cycle: plan, do, check, and act. Okay, and you start out at a certain current state, and you may have a stretch goal. You have a challenge goal somewhere that you want to be in the next 6 months or so to a year. So the first thing that you do, you don't bite this all off at once most of the time. You take little bites of it. So you conceive of an improvement, which is the plan phase. So you have an idea for improvement. You try it out, or you execute it. You do an experiment on the shop floor or at the place where the value is added. You check these. You measure the effect of what you changed. And then based on what you learn, you either establish it, you try something different, or you change it back the way that it was. Okay, the next thing that you do is you verify your improvement. So you make sure that it does what you intended it to do. At Lyle, we add a step for validation. So that means not only does it do what we intended it to do, but there's no unintended consequences downstream. So that requires a second set of eyes to look at the process and just make sure before we establish that as a new way of doing things. And then once we go through the validation, then we establish it as the new standard. Okay, and then hopefully you see we came from the previous state. Now we're a little bit closer. Okay, so now the next topic is, once we've achieved that incremental improvement, how do we sustain it? Okay, so then we do something called SDCA cycle, which is Standardize, Do, Check, Act. So in that, we establish the standard, we deploy the standard work, we audit the standard work to make sure that people are following it, and then based on what we learned during our audit, we address the deviations. So we're going to talk a little bit more later about what these deviations are and some of the ways that you might handle them. Okay, and then we say that the standard work is verified and the standard work is sustained. Okay, so after that, we keep everything standardized until we get around to the next cycle of improvement. So the PDCA cycle continues and continues, but in between PDCA cycles, we want to make sure that we sustain our gains by SDCA. Okay, so where does the information to standardize our operations come from? Well, if we start, assuming that we're starting our standard work process from a rapid improvement event, we'd have a future state value stream map, we have future state time observations, and we have future state work allocation diagrams. And we'll talk a little bit more about what these actually specifically are. What comes out of the event on day 4, when we're standardizing and establishing our new methods of doing things, are our standard work combination sheet, our detailed pictorial work instructions, which have various names. standard operating procedures, graphical work instructions. They're called a lot of different things. And then, of course, we have, as we talked about in our visual management course, we have our visual controls. Things that are actually embedded into the work environment itself to give us direction of what to do next. All this comes through lean analysis and brainstorming, which then leads to improvements. Okay, standard work combination sheets are considered an advanced lean technique. Why? Because you need to understand what all these things are first. You're starting out, a standard work combination sheet includes a layout diagram of the area. It includes a time chart, which shows overlapping time and separation of man and equipment. It contains all the work elements required to do the job, and it requires you to be able to do a pretty sophisticated lean analysis. So what's a lean analysis? Well, we'll look at it in more detail later, but it involves value added versus non-value added, involves a time chart, and it involves operation balancing or line balancing. Okay, so it takes multiple forms. You're doing these sheets for probably multiple families, multiple items, and there's a lot of complexity involved. Okay, so why is standardization difficult? Why is it something that's so hard for a lot of companies to master? Even companies that have a very energetic rapid improvement event program. It's because the teams spend most of their energy in the planning and implementation phases. And when you're in the heat of doing one of these major improvements, the changes seem so real and tangible that the likelihood of the improvements fading, it isn't really on your radar screen yet. You don't really believe it's going to happen. And because of that, it doesn't motivate you. It's not a priority. All the stuff, all the hard work that you did during the event, the time observations, the work allocation charts, carefully collected, compiled, crafted by hand. But then once you start having to duplicate it for every single item family you're running through a cell, or every single item you're running through a cell, starts to become very tedious to duplicate by hand, especially the second or third time. Now, the other thing that happens is when your lean program is based mostly on rapid improvement events, is that by the time the process stabilizes, the key members are back to their regular jobs or they're involved in the next project, and they don't typically come back and make sure that all the details are taken care of in the old events. But what happens when you do this? When you don't establish that discipline? You have reversion to old habits. You have what you'd call unmeasured and unproven innovations begin to proliferate. So these are people with the best intentions as individuals, but they're not doing controlled experiments. So they start out with an improvement. They come up with their own innovations, but they don't have anything to measure it against, and then everything just becomes subjective, and everyone's doing things differently, and everything that you've won just goes to pot. Some method improvements or hard-won insights can simply be forgotten over time. That's just human nature. It's the way human beings work, is that over enough time it could just be ground out of you unless you have a system in place to sustain your improvements. Inconsistencies between operators in the same tasks, or even worse, between shifts, can affect productivity and quality in unpredictable and negative ways. So then what happens, the result of all this is that gains won during events, projects, or shop floor Kaizens can deteriorate instead of stabilizing or further improving. So then you just have a situation where you're doing events just to oscillate. You gain something, it gets lost over time because of entropy, and then you have to regain. Your next event doesn't do any more than just picking up lost ground. Okay, so this is a depiction of it. And you can see the same thing we saw earlier, that you go through the PDCA cycle, you go through the validation cycle, you establish a new standard, you realize your improvement, but then you go backwards because you didn't verify, you didn't establish your standard, and now you've gone back down again. And that's not good. Okay, so what information is required to standardize work? And this is a good question because you don't want to be too prescriptive. You don't want to try to, control the slightest micro motion that everybody's making. But what you want to do is you want to find the minimum information required to sustain the gains and control the process on one hand, and on the other hand, avoid unnecessary bureaucracy or unnecessary prescriptiveness. So a good compromise is the minimum required detail to sustain method improvements in terms of productivity, quality, and safety. So whatever it is, whatever level of detail you use to get the improvement, that's what you have to detail and document to sustain it. Okay, so what are the common standard work formats? Layout diagram showing sequence of operations, safety, and quality concerns. A detailed sequence of steps required to perform each operation in the process, cross-reference with the diagram, standard work in process, cycle time, and takt time, and a lean analysis of the most up-to-date method. And don't worry about all this terminology. We're going to show each step graphically so you can see what all these things are. Okay, so this is just a short example of the work sequence. This is laying out and describing the elements and the element times. Okay, and there's a number of ways you could get this. You could get this from a time observation study. In this case, I used an electronic spreadsheet that I developed myself to take times off of videos. So that's how we do things. So that's the tool that we're using at RW Lyle right now. We also have a time chart. So the time chart shows overlapping elements between operators. So it could show two things being worked on at the same time. And it separates out the elements between working, walking, and machine time. Okay, this is the cell diagram. So the cell diagram, again, this is the Excel tool that I developed, and I just have reusable graphic objects that we drag and drop and rotate around the screen, and we have the little connector lines that join the operations together and show the work sequence. And we also show different configurations for when the cell has like one operator versus 2 versus 3. Some of the summaries that we have here, we use this to get a visual, kind of get an idea of the space that's taken up. The little green cells are the standard WIP. So by putting the cells, by typing the numbers in, and there's conditional format, so it automatically turns green wherever there's a number in the grid. Then we count our standard WIP, and then that gives us, through using Little's Law, that tells us what the lead time is for a part to come in one end and go out the other. Okay, so the next question is what's included in a lean analysis? Well, the important issue in a lean in lean itself is the elimination of non-value-added activities. But we break it down into further detail in the lean analysis. We say that each element has it's classified as value-added or non-value-added, but also we have a type 1 and a type 2 non-value-added. So we'll talk about that in a moment. Then it's also typical to break down element times as working times, walking, waiting, or machine time. So even with working and machine times, you want to kind of show what the overlap is between what's the operators doing and what the machines are doing. Okay, so to reduce waste, we understand that one of the techniques in lean is to, once you have the value stream established, you want to flow the value stream. In order to flow, you have to have your work allocation between operators balanced. That's how you get to this closer and closer to single piece flow. So for that, we're going to show the work allocation chart. Okay, so this is an example of the lean analysis, and you can see you have a certain amount of value added, you have a non-value added type 1, and you have a non-value added type 2. So value added, of course, is anything the customer is willing to pay for. It could be put on an invoice and they would accept it. Non-value added type 1 is strictly by definition, it's non-value added, but it's required in order to do the value-added work with the current engineering design, with the current equipment that you have, and the current legal and regulatory environment that you're operating inside of. So those are things that are very hard to change. Those are things that you would change through engineering design, through process redesign, you would probably not change it at the shop floor. It requires, some stuff to be done in the back office first. Non-value add type 2, on the other hand, is saying, oh, that pallet's like 10 feet away and it could be 2 feet away. It's all the low-hanging fruit. It's all the things that are just purely waste that you could address very quickly and eliminate. Okay, so anytime you're doing a lean analysis, you're looking at what's the relative contribution of each of these things to the total amount of time. Okay, the next thing that you're looking at is you're looking at your work analysis, which is the machine time, the waiting time, the walking time, and the working time. Okay, so based on that, obviously, if you have a lot of walking time, there's certain solutions that would suggest. If you have waiting time, there's certain solutions. And then, just for informational purposes, you want to see how much of what you're doing is machine-based versus labor-based. Now, the work allocation chart, you have your rate of demand, which is your takt time, versus your rate of supply. Now, your rate of supply, if you're in a work cell, operator number 1 is doing his set of tasks within 50 seconds, and you can see operator 2 is doing his task within, say, around 57 seconds. So in a cell, what's going to control the output? It's going to be the longest operation. So in this case, the rate of supply is going to be around 57 seconds. The rate of demand is, say it's around 62, 63 seconds. Okay, so that's the work allocation for this particular cell. Okay, what are the benefits of doing this kind of analysis? Well, when you do the lean analysis as part of your standard work study, you're already setting up the next team or the next person to look at it with an idea of what exactly they should, what are their opportunities for improvement. It's documented right there in front of them. So small and large ideas from the operators, when the operators are trained in the standard work too, they also are prompted. They look at these things. They see, okay, these things are flagged as non-value added. What can I do to improve that? So some of their ideas will be small, some of them will be pretty ambitious, but they should be experimented with, and their effects should be measured against the established standard work. So once it's established, it's perfectly okay to do controlled experiments and see what your results are. If the experimental modifications do not improve on the balance of work, so the work allocation chart, improve safety or improve quality or eliminate non-value added tasks, they should not be adopted. Because everybody has opinions, but we want to have a scientific process engineering basis for changing one standard with another. Okay, if improvements are measured and if they're verified and if they're validated to cause no unintended consequences, they should be incorporated into the standard work, established, audited, and sustained, and then the cycle begins again. Okay, so this is the condition that we started with at RW Lyle. A lot of our the beginning of our standard work program came largely out of rapid improvement events. It's moved on somewhat since then. We have like a massive amount of studies being done now. But starting out from the original events we had, this was the documentation that we started out with. Okay, so from this documentation, we developed our set of standard work combination sheets, and we put them together into these notebooks. And in a lot of companies I worked at up until now, it was always a question, do we hang these things? Do they belong to the operators? Do they belong to the leads? Do they belong to industrial engineering? Who's the owner of it? And then finally, we came to a realization it's simple. It's a playbook analogy. So if you have a mature standard work program, you have all your standard work together in a playbook that describes how the operators are organized and what sequence they move in, and what they do at each station and how much time is allowed. Logically, that's the responsibility of the lead. That's what a lead does at RW Lyle. So they're the ones who make sure when there's a changeover, they set up all the equipment in the right place according to the diagram. They organize the people in the right place. They tell them what workstations they're flexing between. When the operators get to those stations, there's detailed pictorial instructions telling them exactly what to do at that station, but that's point of use. So the operators are responsible for following those instructions, and the leads are kind of responsible for orchestrating the movements around the playing field there. Okay, so the owner of the playbook is the lead of the cell. Now the playbook is organized by part or item families and typical staffing levels. So when a particular item comes up and we want to run at a specific rate, the lead of the cell should be able to flip through the notebook, find the exact standard work sheet that they need, and then just go right away. Okay, so what we call the existing, now it's the old method. We used to do these things in pencil and paper, and there's a lot of proponents of doing it that way, still, because there's more physical ownership of the operators over it. But when you scale up to a certain point, there's no validation. The stopwatch studies aren't perfectly traceable. Sometimes they're ambiguous or wrong. There's no standardization, and there's not a lot of sharing of information, especially if you're in multiple plants or you have multiple cells doing the same thing. You want to have one current best method across multiple production units. The paper-based version has its limitations. Okay, so some of the problems: you have multiple product families. One riser line, we have 31 different product families. So quite a bit of work for the leads to keep up with maintaining all those things. We've never been able to train more than a few leads or technicians at a time to develop those sorts of documents. Most cells don't audit the methods, or didn't audit the methods back then. They didn't adequately explain them to the operators. They didn't always do lean analysis. So a lot of the paper-based ones that we had, it's like some of them had bar charts, some of them didn't. Some of them had pie charts, some of them didn't. Some of them had time charts, some didn't. Some of the diagrams were in CAD, some of them were hand-drawn, some of them were in Excel. So it was kind of a mess, and of course it wasn't tied into the overall enterprise. We had no visibility in engineering of what the people in the shop floor were doing, and vice versa. Something would change in engineering, you'd have to update the standard work, but I'm not sure that always happened because doing standard work by hand is very tedious. Okay, so in the new method, what we've done is we've consolidated all the forms that we used to use into a single sheet. We incorporate video footage in our studies to eliminate any kind of ambiguity. So one of the things that we do as we're validating the standard work, we actually will bring the operators from the cell into a meeting room. We review the footage with them, and we have them actually watch as we develop part of the standard work. So they have a lot more ownership over it versus even the paper-based method. So they're this is what we want. We want them to be their own process engineers. We want them to analyze what they're doing from the outside. And this video footage is like a great way to do it. Obviously, they use it in football when they review plays and footage of the game, and it's a very powerful method. Not something that's typically done in paper and pencil traditional type of lean environments. The other thing that we do, that the electronic system does, it automatically generates the lean charts for you. So it takes, a little bit of that tediousness away. Develop the layout diagrams electronically to ensure uniformity. They're all going to look the same. They're all going to have the same format, so that you're not you're not trying to learn a new format every time you're reading a new sheet. You could focus in straight on the information, on the diagrams, on the work elements and that sort of thing. Okay, and as far as operators participating and updating it, well, it's an interesting thing. When you have these handcrafted standard worksheets, and some of them look like they were made by drafters. They're so professional. People are not going to want to mark those up every time they come up with an idea. And so that's why, we have these beautiful sheets sitting out there. They're 8 years old and have never been updated. And meanwhile, the methods have been improved like dozens of times. So that's why we're converting to an electronic format. We tell the operators, feel free, tear the sheet out of the book, write it, mark it up, take new video footage, send it to the back office, and we process it from there. We have 2 different facilities. One is in Wisconsin, one in California. So now we each have visibility of what the other is doing as far as their current best method in each of their work cells. Stored on the network, anyone can access it. Okay, so the recommended training sequence for somebody who's going to develop standard work from beginning to end. You need to be trained to do time observation studies. You need to be trained to do work allocation charts, which is the line balancing diagrams. The spaghetti diagrams, which is the cell layout with the flow paths showing which stations each of the operators flexing between. You need to understand takt time and be able to calculate it. You need to do lean analysis and understand continuous improvement. We still like to train people to do manual completion of forms, because eventually, some people are going to end up working at a place that don't have an electronic system, or, we want them to kind of get the hands-on feel of it first and get a really deep understanding. And then only once we do all that, then we switch to we train them to use the electronic standard work application. Okay, so how do we define how many studies we need to do? Well, in some cells you have to do a study for every single item. But in other cells we're able to use a form of group technology to define item families. And if we define them the right way, and if we leave our standard work at a certain level of detail and just rely on the bill of materials or the job order that's traveling through to fill in the details of specific items and things of that sort, we can define families that have a wide variety of different items that are identical. They're processed identically, have the same sequence, have the same timing, or at least they have the same timing at the controlling station, so they're going to have the same end result. So it's tricky. If the standard work is identical, it's the same family. So we go through some recursive analysis, and eventually we figure out that certain geometric configurations of parts are going to have exactly the same time standard. And then we could define that as a family, and from that point on we know that all those families are mapped to the same study. Okay, now this is one of the most important aspects of standard work. One of the most important aspects is standard work has no meaning outside the context of PDCA and continuous improvement. It's not the same thing as like in the old days you'd have a work instruction, you'd write it up once, and then it would be your work instruction for the next 20 years. No. It's a live document. It's supposed to be continually experimented against, and it's meant to be constantly challenged and eventually improved on. So it has to be emphasized again, it's only a tool to capture the current best way of doing something and to provide clues for identifying the next improvement. That's why the lean analysis is so important. So don't just let this become something that you're doing for costing or something that you're doing for scheduling. It is, but really it's a lean tool. It's a tool for continuous improvement, and that has to be a very critical, that has to be one of the biggest motivations for doing standard work. Okay, now the question we had when we started our implementation, because we have literally about 8,000 different operations that need to be mapped to a study. And not all the products run every day. So the question they had when we started out like 3 years ago is, when is it going to be done? When are you going to have all the items done? Well, standard work is a discipline. It's not just a document. So there may be things that, we're only going to see it run once every 3 years. You're not going to get those documented very quickly. But the implementation of standard work is complete when the skills are in place, not necessarily when all the part families or the specific items have been documented. So you have to track it by skills and by disciplines, and by having the PDCA and SDCA cycle functioning in every work center where you want to implement standard work. Okay, now in the old manual method of doing standard work, here's the way that cycle works. The lead checks the playbook before changeovers and verifies the employees understand what to do through training or validation. If a new part or item family is encountered, the lead stops what they are doing, works with the operators to develop a logical starting method, records the time observation, completes the standard work combination sheet by hand, and sends it to sustaining engineering for validation and follow-up. So sustaining here at Lyle, it means like an industrial engineer or a manufacturing engineer. Somebody who works outside of product development and supports the shop floor on a day-to-day basis. The lead works with the operators daily to find small improvements to the cycle time, the standard WIP, and the value-added ratio. Improvements are verified at the cell with an updated standard work combination sheet. The updated sheet, again, is sent to sustaining engineering for validation and follow-up. So if you're doing the manual method, this defines a complete cycle that shows that a work cell is doing standard work. As the items come up in the schedule, they get studied. So eventually you're going to cycle through everything that you're actually running. Everything will have a standard work study. But it's important to have that discipline to stop what you're doing and to record these studies, and to record whenever you experiment and find an improvement on a standard method. Okay, now this is one of the other reasons why we went to an electronic system, because you could see the difference in the cycle and how much easier it is for the people in the Gemba. A newer improved method is video recorded, and the lead reviews it with the sustaining engineer. The lead may also mark up a previous computer-generated standard work combination sheet to describe an improvement, such as a layout change. So you're going to mark up the sheet, and you're going to take a new video. That's all that the operators, that's all the people on the shop floor have to do. So it's going to be a lot easier for them to sustain, experiment with things, without having to be too tied up in administrative work. So the sustaining engineer develops a standard work combination form with the cell, reviews it with the operators, and prints out a copy to return to the cell with the playbook. Okay, so this is what we came up with in our implementation, where we started from. The most commonly, the stuff we run on a day-to-day basis or even on a weekly basis, documented within 1 to 2 months. And then you have all the oddballs, the 80% that is less than 20% of our volume. It just pops up from time to time, and we're constantly studying those. The other thing that we're working on is to utilize it for coming up with new concepts for cells, for new product development. There's some amount, once you gather enough work elements, once you gather enough methodologies of doing things, you could do a lot of cutting and pasting and simulate some things. So that's something that we're using the system for on top of that. So that's it for our module on standard work. Thank you very much, and you're almost at the end of the Yellow Belt course. The next course module will be A3 thinking and consensus building. Thank you very much. Bye.